Okay, so for this video, we're still talking the prerequisites for the course. And in this case, we're going to talk the word problems and we'll give you some notes. Later on, we'll do some problems and practice. There's a little bit of practice in here. And then we're going to look at the homework, the extra credit homework is the lecture note practice, which is kind of optional to do, but you can watch the video as we go through the problems so that you at least have a sample of it. But starting right now, we're going to talk word problems. So we're going to talk, they're not really word problems, but they're special cases, the 0, 1, and infinitely many solutions. We're going to talk translating words to algebra. And then we're going to do percent increase and decrease. Those are word problems. And then we have an example of that, and then distance, rate, and time problems, and then an example of a distance, rate, and time problem. So hopefully this will be a not too long video, but I have a tendency to be a little bit more verbose than the PowerPoints. So with 0, 1, and infinitely many solutions, basically you solve the equation as usual. 0 and infinitely many solutions are special cases where the variable cancels out. Basically, the variable's the same on both sides of the equation, and you have to know how to deal with that. So our steps are simplify each side of the equation or inequality, the same as we do with solving regular equations. Move the letters to the one side of the equation. And then when you have moved the letters to one side, the numbers to the other side, you find that you have no variable. Or you notice that both sides of the equation are exactly the same. That's another case that can happen. It is a no solution problem if you end up with something that is blatantly false. So like 4 equals 0, 7 equals 2, those type of things. You've got something that does not equal, then there is no solution. You ended up with a false answer. If you find that both sides of the equation are exactly the same, meaning exactly the same, nothing different, or you end up with 0 equals 0, or a true statement at the end of the equation with numbers equal to each other, then you have infinitely many solutions. It doesn't matter what we put in for the variable, we're going to get the same answer. It's always going to work. And then, so those are special cases. If you have the variable, you have one solution and you solve it just the same way it is. For translating words to algebra, I do this a little bit different. There is a lot of translating where you get the words and what they mean algebraically. I am sure you can find those on Google and you can work with those on if you need terminology type stuff. But the one thing that I do want to note is, and a lot of people think oh, that's how I add. That is always represented by a plus sign. It is not the case. There are a lot of times that your and is going to be a minus sign. But there are specific things that you're looking for to make that happen. So we're going to practice some of those with this. And basically an operation followed by of, I should have that in parentheses. I'll fix that in the slides. So like the difference of, the quotient of, that just means that next and gets that operation. So that is where that and changes. I will work on the wording of that bullet. So for example, you have the distance of a number and 5. What that becomes is x. So the number, the and is a minus because we're talking a difference, and then we have the 5. So a lot of times I will put an arrow saying that, oh, I want to go from the distance, that is an and. A lot of times I will put this underneath it. We'll have a minus sign so that I remember that and is going to be a minus. All right, so anything that before then goes at the end of that expression that we're going to have. Is less than or is greater than, that means an inequality. So if there's an is attached to it, then you have an equality. So you have to be careful with that. Looking with where we have. So like 5 less than 8, you're going to have 8 minus 5. So the 5 has to go at the end, whatever it was in for. 2 operations that are together generally mean that you need to use parentheses or some sort of grouping symbols. For example, if I have twice the sum, twice is 2 times. So I have times and sum right next to each other. That means I'm going to have parentheses. So twice the sum of a number and 3. Sum means plus. So the next and is a plus. So that kind of goes with what we have. And that just becomes 2 for the twice, 2 times. And then I have parentheses n plus 3. All right, so our steps are write the sentence to be translated across your paper. Ideally, 1 row, line. You can get space between the words if you need, but you can get it in one row going across your thing so that you have space above and below your words so that you can draw arrows and all that other stuff. You read the sentence word by word and write the algebraic equivalent beneath this. I know this seems slow, however, it does work quite well. And then you use arrows for a lot of things, telling you if anything moves, I use an arrow. So our example is going to be 5 times the difference of 3 times a number, and 2 is 8 less than 7 times the number. Now, I've highlighted the keywords that I'm thinking about. So I have a difference of, that is going to be meaning the next and gets my minus sign. I'm going to try to do it here. This and is going to be a minus. I can either put it above or below. I will have it typed up, so I'm going to have that. The 8 less than, that means it goes at the end, and it will be a minus 8. Okay, so those are keywords that cause problems on things. All right, so then we have, looking at that 5, right underneath it, I have a 5. Times, I have a star for my times, where I'm talking about it, times and difference. I have parentheses started because there's 2 operations right next to it. The difference, I have moved to the and, so I'm skipping that, and I did my arrow. 3 times, so 3 times is a star. A number, I'm using n for my variable, and that became the minus because I told myself it was a difference of. 2, just a 2, is equals 8 less than, that went to the end. So as you see it, it's the 8 less than, and I have it highlighted to match with that. 7 times the number. And then what you do, once you have it with everything worked out with that, I just combine it together so that you can see it all without those extra spaces. It gets a little confusing, getting rid of the stars that I don't need for multiplication because of the implied multiplication. And I have 5 parentheses 3n minus 2 equals 7n minus 8. And a lot of times I would have to solve it from here, but that is how I've translated it, going with that. So I've got that. And we're going to go to percent increase and decrease. Now, this is a formula. It is, different people will separate the percent increase from the percent decrease. However, I use the same formula for both because I don't like to memorize a lot of stuff. And percent increase and decrease, a lot of times it will be, you'll do this in biology or a science class where you're looking for the rate of change, that kind of stuff. It's also called that. I can put that in my notes if I can find my mouse. Yeah, this is also called rate of change. Ooh, my handwriting is terrible today. Anyways, so when I'm thinking about it, if I use the same formula, I just remember a percent increase, my answer is going to be positive. Percent decrease, my answers are going to be negative. And what I do is use my formula, which is new minus old divided by old. That will give me a decimal that I might need to change to a percent, depending on the question. It always goes back to, what do they ask me for? Do they want a decimal? Do they want a percent? What's going to be useful? And just remember, if decimals are always smaller than percents, and you always move the decimal place 2 spaces. So if I want a decimal from a percent, it's always going to get smaller, so it'll move to the left. If I have a decimal and I need a percent, the decimal point will move to the right, and I will end up with a bigger number. All right, so for my example, I erase everything. Clean sheet. Not a clean sheet, but that's okay. Rate of change, remember, it's percent increase or decrease. We've got the formula, and I've got problems with my animation, so we're just going to click all of it, and I will work with that later. So my problem is, last year a local gym had 100 members in January. In April, the gym had 75 members. Typical of what happens because of New Year's resolutions. What is the percent decrease from January to April? So looking at that, I'm still using the formula new minus old divided by old. My new is going to be my April because that is the later date, and that has 75 members. My old is January, which had 100 members. Putting that into my formula, the new, so it's 75 minus 100 divided by 100 gives me a negative 25, which makes sense because I've got fewer members. It is a decrease. It's going to be a negative number. So negative 25 over 100. If I reduce that fraction, I get negative 1 over 4. If I divide it out, I get negative 0.25, which is, move the decimal 2 spots, 25%, because percents are always bigger than decimals. Now, hopefully you also recognize that a percent is per 100. So this fraction, the 25 over 100, is also giving you your percents. All right, so now, distance, rate, and time. A lot of people have problems with these because they are bigger word problems. Just the general thing that we know with distance, rate, and time is distance equals rate times time, which we commonly write as d equals rt, looking with variables and stuff like that. So when reading a word problem, there's a bunch of different ways to do it. It's important to read the question thoroughly, completely, once for sure. Kind of taking it a little slow. You can take notes as you're doing with it, but it's really the key with word problems that I've found is if you read it sentence by sentence and say, what does this sentence tell me? Every sentence will tell you something. It might be the equation. It might be what you're dealing with in the problem. It might be some bit of information of a specific number that you need for the formula. Generally, the last sentence will either tell you what you're looking for, so what variable you want to have. It could give you the final equation that you're dealing with. And it could also tell you what formulas and stuff you're going to be doing with. So throughout the problems, we're going to be getting a lot of information, one sentence at a time. I tend to read a lot really slow when I'm looking at them. All right, so you can solve for other variables of distance equals rate times time. Basically, you know whether or not you're going to use it. So if I'm solving for r, I would divide both sides by t. So I have r equals d over t. If I was solving for t, I would divide both sides by r, and I would have t equals d over r. We will be using these equations later in the semester. But for the most part, we're going to be dealing with, at the very beginning, just d equals rt. And the way that you know which format you want of that equation is if you have two things that are the same in both situations of the problem, then it's going to be easiest generally to use the form that has that letter, that variable solved for. So if you have the rate of things and you're told that something happens at the same time, then you would probably have use the t equals d over r. But we're going to talk about that much later as we get into the semester. So we have an example problem with d equals rt. So we have two cars leaving. This is everybody loves cars moving. So two cars leave towns 750 kilometers apart at the same time and travel towards each other. So one car rate is 12 kilometers per hour, less than the others. If they meet in 5 hours, what is the rate of the slower car? So if I'm looking at this, I know I have information that I know. I have two cars. Slow. Well, actually two cars. That's the first bit of information. We'll do this in order. So let me erase that. Two cars. And we know that in the first sentence, two cars leave town 750 kilometers apart. So D equals 750 kilometers. This is a total because the two sounds are apart at the same time and travel towards each other. So time equals same. Okay, one car's rate is 12 kilometers per hour less than the others. So I have a slow car and a fast car. And the difference is going to be 12 kilometers per hour. I'm going to think about that in a second. I'm going to underline that to remember it. Actually, looks like I crossed it out. I really don't like that. So my pen doesn't work too well today. Okay, so I have my 12 kilometers. That's off. Fabulous. I'm going to go with the squiggle. That's going to be my safest. All right, less than the others if they meet in 5 hours. So I now know that T equals 5 hours. What is the rate of the slower car? So I need slow car. So slow rate equals R. So a lot of times we'll have a comparison, and whatever things are compared to, that's what gets the variable. But in this case, what is the rate of the slow car? They're asking for that. That's what I want to be talking about. All right, so then I've got some of the things already written out based on how I read the equation. How I would organize it for my problem is going to look like this. Since there's the only thing that's the same for both cars is the time. I don't know the distance, like each one separately. I know a total distance, and I know how the rate kind of combines with each other. I'm just going to use the general D equals RT because I also have the data I have is a total distance. So I kind of want that by itself. So what we know is we know the total distance. And if you know totals, you know that you're adding two things together. What two things do we have? We have the slow car distance and the fast car distance. So I know the slow car distance plus the fast car distance equals 750. So when you do have word problems, there's a little bit of assumptions that you have to, it's assuming you have some past knowledge and that you can define some stuff. So distance, when they're saying between the two towns, you have to know that that's a total distance and it's made up of the slow car's distance and the fast car's distance. The slow car, I know my rate is R, which means the fast car, it's got to be 12 kilometers an hour, but it's got to be faster. So I'm going to go slow car plus 12 kilometers per hour, which is R plus 12. The time for both of them, it's 5 hours. And that came from this thing. The distance, I'm going to put it into the formula. So I have distance equals rate times time. So for the slow car, it's going to be R times 5. I like the number to be in front, so I'm going to say that's 5R. So this is the distance I'm going to put in here. I should have probably typed it, but I might update it. This is the distance of the slow distance. This is my fast distance. So looking at that distance is the rate of the fast car, which is R plus 12 times 5. I'm going to put the 5 in front of the parentheses. It doesn't really matter looking with that. And then I'm going to take that first sentence, that total distance, which is that information, that equation that I have to fill with, and I'm going to put the slow car's distance and the fast car's distance into that formula. So off to the side, I have my equation from the total distance. Remember, it's slow car distance plus fast car distance equals 750. So I have 750. This is my slow car, which is the 5R. And the fast car distance is 5 times R plus 12. Now this is what I'm going to solve. I don't show all the steps in my work, but some of it, we're going to explain it. So first thing I'm going to do is distribute that 5 in the second equation. So it's going to be 5 times R. Oops, wrong button. So 5 times R, which is 5R, and then 5 times 12, which is 60. And then I am going to combine like terms. So I have my 5R and my 5R gives me the 10R. Still have that plus 60. Then I'm going to subtract 60 from both sides. I don't write that, but I do it. Looking at that, I have 690, so 750 minus 60. A lot of times when my equations get really messy, I need to show that because I will forget signs. I am notorious for changing positives to negatives and forgetting that I have that stuff. And then I'm going to divide both sides by 10 because I want to get rid of that coefficient on the R. And I get R equals 69 kilometers per hour. And that is my slow car. So I have answered the question that I have been asked. Sometimes I will be asked for both of them. So if the slow car is 69 kilometers per hour, the fast car is going to be 81 kilometers per hour. No, yeah, 69 plus 12. Yeah. So that is how we are going to solve that. And that will be it for this video. The next video that will be in the module will be going through the note problems from Alex.